Hello, this is Mr. Boston. We'd like to go over an energy conservation problem here. This one's a little bit sophisticated. We have a box here that's going to be sliding down a ramp, and then it hits a rough patch, and there's some friction that happens, and then it squishes the spring to a stop. Okay, so let's give it a read and try it out. So a box of 2 kilograms slides down a frictionless ramp. Then when it initially has 1 meter per second of speed, and then onto a flat rough surface and collides with a spring as shown in the diagram, right? If the coefficient of kinetic friction is 0.4 and the spring constant is 25 newtons per meter, then how far does the box compress the spring? Okay, so I guess the first thing I'd like to do is try to identify what our energy transformations are going to be, and if our system is isolated or non-isolated. So I see a spring, and I see a box that's moving, so I think my system is going to be these things. It's going to be the box, because it has motion energy. We're going to study how that moves, and the spring. And I think it's going to be the Earth. We have a height change, so the Earth is pulling on it, and it's going to be um, producing heat with the ground there. So I think those are things here. And so, having said that, I think it's going to be an isolated system, and let's look at this in a little bit more detail here. So at this point, I'm going to label the types of energy. Maybe halfway down the ramp, I'm going to label the types of energy. At the very bottom of the ramp before it starts sliding, maybe part way to the spring, and then when the spring finally gets fully compressed, okay? And so let's just say I'm going to add those energy conservations. We're going to add those labels up here. Okay, so I'm going to define the lowest point as my initial height, well, sorry, as my height of 0. I'm going to measure everything up from there. So when it comes down here, I'm going to have no potential energy due to gravity. Okay, so I'm going to have some UG to start with, plus it's moving, so I'm going to have a little bit of kinetic energy there. As it goes down the ramp, it's going to get speed and lose potential energy due to gravity, so it's going to go still some UG, but maybe that's transferred more into kinetic energy. And at the bottom of the ramp, I've given up all my UG, and it's turned into kinetic energy. And I haven't started scraping yet. Now, as I go across, it's going to be going to here. And so now I'm going to start losing some of my K, but I'm going to start producing some thermal energy or heat. And by the time I get all the way to the spot where the spring stops me, and maybe it pushes backward, but it's going to come to a stop for a moment in time, I'm going to have, it's going to be going, and it goes boing, but it's still scraping here. So I'm going to have, I'm going to produce some US. I'm going to still have that heat that's been generated. The heat from here and the heat as it scrapes here, all that heat is still in my system. Okay, so those are our energy transformations. As we go towards the spring, it's going to do all these different things. And the key here is, when we're doing conservation of energy and we're applying it, what 2 points at a time do we want to use to solve for stuff with? And so I think we're going to have an isolated system, and that we should probably use this, because we'd like to understand how much the spring compresses. This point contains my unknown that I want to solve for. And I'm never told any information about the speed of the block during these points, but I do know everything about where this is. I know how high up it is, and I know how fast it's going. So we're going to include this because it has lots of known information. And so basically, this potential energy due to gravity and this kinetic energy I have initially is going to eventually transfer into thermal energy and spring energy. Okay, so I'm going to go ahead and roll with that for my energy conservation of energy equation. So how do I get to my final energy state? Well, that depends upon how you started, what energy you started with, plus what you did to change it. And we're saying that in this particular situation, we are an isolated system, so we had no work done on our system. So basically, our initial energy is equal to our final energy. Let's go ahead and put in the details of that. Next line, we're going to say, hey, I started with some UG initial and some K initial. And that's going to transfer into some US plus some thermal energy we're going to develop from the heat as we're scraping across here until the spring stops us. Okay, so let's put in another line of detail here. So UG initial is just going to be MGH initial plus 1/2 MV initial squared. That turns into spring energy or elastic energy, Kx squared plus my thermal energy. So I want to just spell out how that works, thermal energy. So let's look at thermal energy. So thermal energy is basically the work done by friction. That's how I describe it. So force times distance kind of thing. And we know that friction is equal to mu times n. How rough your surfaces are and the squeeze of those surfaces together produces your friction. So we can substitute those in here for friction, our friction force. So mu times n is what that friction force is equal to. We still have our d. And we can also say, hey, normal force in this case is just equal to the weight, which is equal to mg. So when this block it gets down here on this friction surface, it's got mass, so gravity pulls it down with some weight. And normal force is going to be acting upwards. And I'm only drawing my vertical forces here. We're ignoring everything that's happening horizontally just to keep this simple. And so my acceleration in the vertical y direction is actually equal to 0. It's not levitating off or submarining into the ground. And so that just means my normal force is equal to mg, basically. That's what I'm saying here. So we can say, hey, mu, instead of n, we can put mg in that place. And we still have d here. And so, yeah, let me just highlight what we did here. Okay, so we said thermal energy is basically the work done by the friction force. Okay, so force times some distance, and we're going to call maybe the distance that it scrapes along here until it stops right here is going to be capital D. Okay, and so friction is just mu times n, so we substituted that in there. And then we saw, hey, normal force is just mg, so we substituted that in. So basically, we get our thermal energy is mu mgd. So let's go ahead and put that in our equation. So mu mgd. But now we have another little hiccup here we got to talk about. What's this distance d? This distance d from here to here is d. I'm going to go ahead and clean this up. And so our distance d that it scrapes all the way until that spring stops it is going to be this distance before it hits the spring plus our spring compression. It's going to even scrape during that spring compression too. So d is just equal to lowercase d plus x. And we know that this is 1.6, so it's 1.6 plus x is equal to d. And so we're going to put that in right here. Let's just show that real quick. Okay, so we went ahead and put in that this for d here. Okay, now at this point, boy, it's kind of busy. We got a lot of different energy transformations going on, but let's go ahead and put in the details and see if we can figure out an answer. I'm going to go ahead and just identify what I have to work with. I should have done this at the very beginning, but I have mass m. This is going to be my VO. There's my coefficient of friction. There's my spring strength, and we're looking for the compression. That's our goal. I'll make that important looking, okay? Now we're going to put in the details. Holy cow, this has lots of good surprises here, lots of little details. So we weren't directly told the height that it came from. We were told the length of the ramp and the angle. So I want to just do a little side job here too. So I can find that height for this little right triangle that we can make here. So this is going to be the opposite side leg from this 30-degree angle. And so sine of 30 degrees is h over 1.25. And so I can get that the h is 0.625. So, had to find that real quick. Let's plug in the rest of our stuff. Okay, I've plugged in all these facts here. So here's your UG, MGH. Here's your kinetic energy, here's right here. I kind of wrote it in a waterfall stagger because I felt I was going to run out of room, sorry. And so those two energies are going to be equal to what our spring potential energy, 1/2 kx squared, and our thermal energy, which is shown right here. Ooh, that looks nasty. It's a big ball of stuff. But actually, this whole left side is just one big number. And so let's just consolidate all these numbers real quick. Okay, so I consolidated this. This is all of our initial energy is 13.25. Our spring energy turned out to look something like this. We're not sure how much that spring compresses yet, but we can simplify that. And our thermal energy, when we multiply the stuff out, and we get a number and distribute to this 1.6 and then to this x, we get this stuff. And this looks like a quadratic. And so we can plot and make this a quadratic by moving everything to the right side and getting equal to 0. And we can graph it on our graphing calculators and just find where the 0 is. And so I'm going to show how to do that. So I moved this 13.25 to the other side by subtracting, and that sets 0 equals this stuff. And I can graph this in my calculator. Y equals this stuff, and where it's equal to 0 is where my solution is for x. And I typed this into a grapher called Desmos. So I typed that in. So this stuff is equal to the graph here. And I want to grab my positive number, and I get basically 0.08 meters out of here is my solution where I have a 0 on this graph. And so that's my answer, 0.08. So when I graph this, y x graph, that goes something like this. And this is at 0.08 is equal to x. That's my answer. So even though this is kind of a nasty, and it had lots of nasty expression we came up with, and it had lots of stuff, we could multiply it out, and then this doesn't look nearly half as bad when we see, oh, that's just a quadratic, and we can just simply graph that expression and find the 0, and we got our answer. So this is 8 centimeters, which there's about 2.54 centimeters per inch. So I don't know, it's something, it squishes the spring about this much, which is a noticeable amount. And I would like to plot our energy bar charts for this real quick. So this will be a little more interesting look at what and to produce a visual display of how our energy transformations worked here. So I'll give that a shot. Okay, and so these are the energies I got, and there's a little bit of rounding errors here, but that's okay. We'll get a good idea what happened with our energy stuff. So when I take this and I plug it back into these equations up here, I can calculate what my individual energies were for spring and thermal, and I got the following energies. My initial kinetic energy was a 1 joule. UG was around 12.25. US was very little. It was actually, strangely enough, the energy was 0.08 and the displacement was 0.08, but that's in meters, right? This is in meters right here. And this is in joules. Then I got a thermal energy equal to 13.2. I know these don't add up to be totally correct. There's very close though. We had some rounding errors, but let's go ahead and graph this and get a good visual display of what happened. So I'm going to go ahead and rule out some stuff though. So we know initially our spring was not compressed. We said this is an isolated system. When the spring stops the block at its maximum compression, or it's not moving at that moment, I'm at my lowest energy level, which is height 0, so no UG. And so now I can plot my bars here. And so I had, let's label our axes here real quick. Okay, so this is 4 joules, 8 joules, and 12 joules for these lines here. So we had 1 joule of kinetic energy, which would be something like this maybe. And then we had 12.25 joules of UG, so a lot, so much more, something like that. And then we had some spring energy, just a little, just barely any, to be honest. And then we had, but nevertheless, we did have some. And then we had some, pretty much all of it was our thermal energy produced. So these two energies combined to produce a little bit of Spring's energy, but mostly went into producing thermal energy. So that's a nice visual of what happened. And you know, we end up solving for the spring compression, but boy, this just looks like a big ornery mess of numbers. But this really helps us kind of visualize what happened actually with the energy transfer. So I hope this shows you how to handle kind of a complex energy conservation problem that has multiple types of energies involved, but nevertheless, it was an isolated system. So thank you, and I hope that was helpful.